Hey, 17B students, here are the solutions to the second practice exam that I wrote. All right, problem 1a. Find the partial fraction decomposition of the rational function f of x equal to x squared plus 13x plus 16 divided by x times x plus 2 squared. So we're going to have three pieces in our partial fraction decomposition. A over x plus b over x plus 2 plus c over x plus 2 squared. Try some debris over here 1 second. Okay, about that. So now we're going to multiply both sides by the common denominator. So we're going to get x squared plus 13x plus 16 on the left. We're going to get a times x plus 2 squared plus b times x plus 2 plus c times x. Pick your convenient values of x. I'm going to pick x equal to 0. If x is 0, I'm going to get 16 on the left. I'm going to get a times 4 on the right. Because that's going to be 0, that's going to be 0. So we're going to get 16 divided by 4 is equal to a. So that means a is going to be 4. If x equals -2, then we're going to get -2 squared, so 4. 13 times -2 is -26 plus 16. On the right-hand side, a times 0 plus b times 0 plus c times -2. So that's going to lead to, let's see, -6, right? So that's -22 plus 16 is -6 equals -2c, and dividing both sides by -2, we get 3 equal to c. Now you have a choice. You could either pick another value of x, like 1, and plug it into both sides along with the values of a and b. So we can do that. X equals 1. We're going to get 1 plus 13 plus 16 equals a, which is 4, times 1 plus 2, which is 3 squared, plus b, which we don't know, times 1 times 2, sorry, 1 times 3, plus c, which we do know, times x, which is 1. So 1 plus 13 plus 16 is 30. On the right-hand side, we have 4 times 9, which is 36. We have b times 3, and we have 3. So that's 39. So 30 minus 39 is going to be -9. So -9 is equal to 3b. And dividing by 3, we get -3 equal to b. Another way of doing this, which I prefer, would be to equate coefficients. So if you look here, you look at the coefficient of x squared on both sides. You can see on the left-hand side, there's a 1x squared. On the right-hand side, there would be an a times x squared, but a is 4, and a b times x squared. And since the amount of x squared on both sides has to be the same, 1 has to equal 4 plus b, which means that b has to equal -3. Technically, to finish this answer, we should actually write the values in here. So we should say this is going to be a, so 4 over x plus -3 over x plus 2 plus 3 over x plus 2 squared. That's our final answer. All right, next one. Express the following improper integral as limits of proper intervals. Do not evaluate the intervals. So we have to break this up. Well, we do have to break this up because in addition to an infinity being a problem, so is 6. If you plug in 6, you get division by 0. So first we're going to break this up as the integral from 2 to 6 of x plus 1 over x squared minus 36 dx plus the integral from 6 to infinity of x plus 1 over x squared minus 36. But then we actually have to break up this integral again because a single integral can only have one problem at a time. And this integral has both 6 and infinity as a problem. So we're going to rewrite this as the integral from 2 to 6 of x plus 1 over x squared minus 36 dx plus the integral from 6 to pick any number you like that's bigger than 6. I'm going to pick, I would normally pick 8 because 8 is kind of my favorite number, but 8 kind of looks like infinity. So I'm going to pick something like 9. Or the 7 would be fine, or whatever you like. Of x plus 1 over x squared minus 36 dx plus the integral from 9 to infinity of x plus 1 over x squared minus 36 dx. Now we're going to throw in all the limits. So these are the numbers or the expressions. They're going to get replaced by letters with limits. So we're going to have the limit as b approaches 6 from the left-hand side, because we're doing 2 and 6, we're less than 6, of the integral from 2 to b of x plus 1 over x squared minus 36 dx, plus the limit as a approaches 6 from the right-hand side, because we're between 6 and 9, we're bigger than 6, of the integral from a to 9 of x plus 1 over x squared minus 36, plus the limit as, you could also still use b again, or you could use a different letter if you feel like you shouldn't use b again. I'm going to use b again. The limit as b goes to infinity of the integral from 9 to b of x plus 1 over x squared minus 36. They did not ask us to say if it converges or diverges. They did not ask us to do anything other than just set it up. Cool. On to the next one. Yeah, maybe. Cool, on the floor. All right. The next one says the velocity. Oh, the next one says the velocity v of blood that flows in a blood vessel with radius capital R and length L and a distance lowercase r from the central axis is v is a function of lowercase r, so r is our variable, is equal to p over 4 eta L times capital R squared minus little r squared. P is the pressure difference between the ends of the vessel, and eta is the viscosity of the blood. Cool, lots of words. Find the maximum velocity of the blood. Great. So if this is the velocity function, the way we maximize a function is by finding where its derivative is equal to 0. So we're going to take v prime of r. This is a constant. It's just going to hang out p over 4 eta L. And then the derivative of r squared minus little r squared is going to be 0 minus 2r. And if we set that equal to 0, we're going to end up getting r equal to 0. Is this a maximum? Good question. So you could either use the first derivative test. I'm going to use the second derivative test and say, great, v double prime of r is equal to, well, this constant still hangs out, and the derivative of negative 2r is negative 2. If I plug in 0, there actually isn't a place to plug it in. That's fine, though. So note that v double prime of 0 is negative 2p over 4 eta L. All of these constants are supposed to be positive, meaning that this second derivative is for sure negative, which means the function is concave down, which means we have a maximum. So r equal to 0, it does indeed maximize the velocity. Next question. Find the average velocity with respect to r over the interval. Oh, sorry, there should have been a 0 there. I apologize. I will fix that. Sorry about that. Over the interval from 0 to capital R. So that means we're going to, average velocity is going to be, so average of a function is going to be equal to 1 divided by the length of the interval times the integral over the same interval of our function. Where r is, again, the variable of interest. So in this case, I think I might have fixed that. I'll double check though. So this is a constant, just hangs out. So we have the average is equal to 1 over r times p. Make sure your r and your p don't look too similar here. Don't want to accidentally cancel them out. 4 eta L. And then we're going to integrate r squared minus r squared. Capital R squared is a constant on its own. Its integral is going to be r squared times the variable little r. Minus little r squared is the variable squared, so its integral is going to be r cubed over 3. From 0 to r, we're going to plug in. We're going to get 1 over r times p over 4 eta L times r to the third power minus r to the third divided by 3. If you take something and subtract a third of that same something, you're going to be left with 2/3 of that same something. So this is going to equal 1 over r times p over 4 eta L times 2/3 r cubed. And I should cancel this r with one of those r's. So my final answer is going to be, I also cancel a 2 here and a 2 here. So I'm going to have p times r squared over 2 times eta times L times 3, which is 6 times eta times L. That's it. It's kind of annoying a problem because there's lots of like constants that are letters, but it's very doable if we just keep it together. Next problem. That's a lot here. Sketch the region R enclosed by the graphs of f of x equal to 1 over x, y equal to 1/9, which is the horizontal line, and g of x equal to x squared on the interval from 1/3 to 9. So 1 over x looks like this. Y equals 1/9 is just a horizontal line. And if y equals 1/9, we can kind of see that, oh, if 1/9 equals 1 over x, x has to be 9. And then g of x equal to x squared will look like this. I feel like I might have come up with something kind of funky here. That's fine. And then x squared looks like this. I feel like I'm throwing my own self off here. And y equals x squared. G of x equals x squared, sorry. And that's certainly going to intersect that line at x equal to 1/3. There's your region. Bounded by y equal to 1/9, y equal to x squared, and y equal to 1 over x. And the x bounds are from 1/3 to 1/9. And you notice that, right, if you plug in 1/3 for x, 1/3 squared is equal to 1/9. And then find integrals representing the area of the region. Do not evaluate the intervals. So you could either answer this question in one of two ways. You either choose to use a vertical strip where you have to break it up. So I'll point out here that at this point right here is where x squared equals 1 over x, and x squared equal to 1 over x means x is going to have to be 1. So that point there is the point 1 comma 1. So you could either do it as two integrals with respect to x and say, great, it's going to be the integral from 1/3 to 1 of the top function x squared minus the bottom function 1/9 dx plus the integral from 1 to 9 of the top function, which is 1 over x, minus the bottom function, which is still 1/9. That's certainly one way you could do it. Let me zoom in a little bit so you can see that a little better. Sorry. Right, so this area from 1/3 to 1, this area from 1 to 9. We have to use two different integrals because our top function changes. Or you could do this area with respect to y. You could say, I'm going to do the integral from the low of y equal to 1/9 to a high of y equal to 1, and then it's going to be the right function minus the left function. If y equals 1 over x, then if you solve for x, you actually do get x equal to 1 over y, minus, if y equals x squared, you get the square root of y equal to x dy. That would be an alternative way of writing the area. Either one of these would be acceptable. I will point out, though, that for the rest of the questions, where we're talking about finding the volume, since our axis of rotation is the x, well, actually it depends on axis of rotation. So yeah, good to go. So set up the integral or integrals that represent the volume of the solid obtained by rotating the region are about the x-axis. Do not evaluate the integrals. If we're going around the x-axis, we know we're going to have to use the washer method since our region isn't flush with the axis of rotation. So I'll just point out, I'm going to draw my picture again, but kind of less complicated here. So here's my region. There's my region, and I'm going around this axis here. So if I draw a strip, my outer radius is that, my inner radius is 1/9. And then if I draw a strip over here, and again, right, this is the function x squared over here. This is the function 1 over x over here. I draw a strip here, my outer radius is going to be that, my inner radius is going to be that. So certainly having set up this in terms of x here actually helps us because I can see, well, I'm still have the same limits of integration, but now I'm just going to have kind of different functions. So for the volume, it's going to be still the integral from 1/3 to 1, but now instead of top minus bottom, it's the outer radius squared minus the inner radius squared. So it's x squared squared minus 1/9 squared dx. And then we have a pi out in front, right? Because it's pi times the area of the washer. Pi times it's pi times the radius squared to get the area of the circle. Plus, then we have the second one where we're doing the integral from 1 to 9, still a pi out in front. 1 over x squared for the outer radius minus 1 over 9 squared for the inner radius. Cool. All right, now we're going around the y-axis. I think I didn't do a very good job of drawing my region here. Let me try and draw it a little bit better this time. Now we're going around the y-axis. Oh, my light went out. Sorry, I gotta 1 second. I accidentally covered up the sensor. There we go. So, using a horizontal strip now. The outer radius is the function that's further away. So my outer radius is going to be the 1 over x function, except it's 1 over y. And the inner radius is going to be the square root of the xy function, which is the square root of y. So still washer method, but because we're missing this inner part here. The volume is going to be pi times the integral of the outer radius squared minus the inner radius squared dy. The lower limit of integration is the same as it was for what we did here. So the lower limit is going to be 1/9. The upper limit is going to be +1. Finally, set up the integrals that represent the volume of the solid timber working in the region about the line x equals 9. So now we're going same region, but now we're going around this vertical line here. So if my strip looks like this, then my outer radius is going to be that. The difference between 9 and my function there and my inner radius is going to be that. So the volume is going to be pi times still the same limits of integration for doing it in terms of y. My outer radius is 9 minus the further away function, so it's 9 minus the square root of y squared, minus my inner radius squared is 9 minus 1 over y squared. Oh, sorry, you didn't see any of that. I apologize. Let me say it again. So my outer radius is the difference between 9 and my further away function, which was my square root of y function. So my outer radius is 9 minus root y. My inner radius is the difference between my axis of rotation and my closer function, which is 1 over y. So it's 9 minus 1 over y. So my total volume is pi times my outer radius squared minus my inner radius squared. And then we're integrating from as low as y equals 1/9 to as high as y equals 1. Let me zoom back out so I don't make that mistake again. Okay, so moving on. Next question says, let y prime equal 5y times 2 e to the y minus 1. Find all equilibria and use the local stability criterion to determine if each is locally stable or unstable. So to find the equilibrium, we're going to set this whole thing equal to 0. So 5y, I feel like this looks I feel like it's printed weird. Oh well, anyway. So 5y times 2 e to the y minus 1 equal to 0. So we're either going to get y equal to 0 or 2 e to the y minus 1 equals 0. 2 e to the y equals 1. E to the y equals 1/2. Y equals the natural log of 1/2, which I'll point out is equal to the natural log of 1 minus the natural log of 2. The natural log of 1 is 0. So I want you to know that this is a negative number. And usually we call these hat. So y hat is 0 and y hat is negative natural log of 2. Now we're going to use the local stability criteria. So we're going to take some derivatives, take the derivative of this whole thing, and then plug in our critical points to see if the derivative is negative, meaning stable, or positive, meaning unstable. So this is like our g of y, and then we're going to define g prime of y and use the quotient rule, the product rule. So it's going to be 5 times 2 e to the y minus 1 plus 5y times the derivative of 2 e to the y minus 1 is 2 e to the y. Um, yeah. So if we plug in 0, g prime of 0 is going to be 5 times 2 e to the 0 minus 1 plus 0, which is going to be 5 times 2 minus 1 is just 1, so 5 times 1 is 5. That's positive, so we know that 0 is unstable. Plugging in negative natural log of 2, or actually it's probably going to be easier, right? Is natural log of 1/2. G prime of natural log of 1/2 is going to be 5 times 2 e to the natural log of 1/2 minus 1 plus 5 natural log of 1/2 times 2 e to the natural log of 1/2. E to the natural log of something is just a something, so we're going to be getting 5 times 2 times e to the 5 times, sorry, parentheses, e to the nat 2 times e to the natural log of 1/2 is just 1/2 minus 1. That's going to be 0 plus 5 times 2 is 10 times natural log of 1/2. And e to the natural log of 1/2 is 1/2. And natural log of 1/2, as we saw before, is negative. So this is going to equal 5 times natural log of 1/2, which is negative. So we know that this one is going to be stable. So negative natural log of 2 is stable. All right, next problem. Find all equilibria of the autonomous differential equation y prime equal to y times 3 minus y squared times 7 minus y. Construct the phase plot. Sorry about that. That should say phase plot. Complete the phase plot by locating the equilibria and indicating the direction in which y changes on the horizontal axis. Determine the stability of each equilibrium. Okay, so horizontal axis is y, vertical axis is y prime. We have equilibria are going to be 0, 3, and 7. Just setting that equal to 0. We can see that if you pick a number bigger than 7, this is positive because it's squared, and this is negative, so it's going to be negative over here. And then between 3 and 7, it's going to be positive because you plug in 6, it's going to be positive, positive, positive. And then between 0 and 3, it's still going to be positive because it's going to be like plugging in 1, positive, 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 and then left of 0, it's going to be negative. So it looks something like this. And we know that when the derivative is negative, y is decreasing. So when it's negative here, it's decreasing this way. Negative over here, it's decreasing that way. When it's positive, it's going to be increasing. So I would say that y hat equal to 7 is stable. Y hat equal to 0 is unstable. And y hat equal to 3 is also unstable. Because not all of the arrows are pointing towards 3. That's it. A population is modeled by the differential equation dn dt equal to 1.5 times n minus 600 times 1 minus n over 1,000. Find all equilibrium. So set the whole thing equal to 0. And I think it should be pretty obvious that you're going to get n hat equal to 0, n hat equal to 600, and n hat equal to 1,000. I don't think you have to show any more work than that. Oh, I should set it equal to 0, though. So those are my equilibria. For what values of n is the population decreasing? So when is this derivative negative? Well, it's probably the easiest to figure this out by actually drawing the phase plot again. So if I draw the phase plot here, and dn dt. And I have equilibrium at 0, 600, and 1,000. Pick a number bigger than 1,000, like 2,000. 1 minus 2,000 over 1,000 is 1 minus 2, which is negative. 2,000, that's going to be positive, that's going to be positive. So positive, positive, negative means it's going to be negative over here. So down here. And then since each of these factors has an odd power of 1, the sign's always going to change. We're always going to cross. So it's going to be looking like this. So I would point out that dn dt is negative when either n is between 0 and 600 or when n is bigger than 1,000. And that's actually the answer. We could say it a different way. N is decreasing when n is in the interval 0 to 600 union 1,000 to infinity. It's another way you could write the answer. I like this better though, personally. What will happen to the population after n equals 500, to the population after n equals 500 as t goes to infinity? So if we start at 500, we're going to get pushed towards 0. So I would say that the limit as t goes to infinity of n of t is equal to 0 if n is equal to 500. Because if we're starting at 500, right, we can see that, oh, right, we know that n is decreasing right there. So we're going to be moving to the left. Yeah, that's kind of it. Okay. Ugh. The base of a solid is a circular disk with a radius of 5. Find the volume of the solid if cross-sections perpendicular to the base are semicircles. Sketch the base and the cross-section and simplify your answer. Okay, so the base is a circle, radius 5. And the cross-sections perpendicular to the base are semicircles. So like, here's my little cross-section, and there's a semicircle popping out this perpendicular. And if you drew it more, if you like flatten this out, so there's your circle of radius 5, then here's my semicircle like that. That's the idea. Okay, so we need to find the volume of this shape. So here's what I point out. If you think about like a little slice of a semicircle, to just be poorly here, the volume of one of my semicircle slices is going to be 1/2 pi times the radius squared times the thickness, which is probably going to be dx. Okay, so where is that all coming from? Well, area of a semicircle is just half the area of a circle. So I got half of pi r squared times dx, because I'm thinking of this little strip here as having a small change in x. I need to find the radius, though, in terms of my variable x. So I know, oh, look, this x plus this radius, if I label this as x and this is r, I know that x squared plus r squared is equal to 5 squared. So that means r squared is equal to 25 minus x squared, and I can replace r squared with exactly 25 minus x squared. So the volume of my slice is 1/2 pi times 25 minus x squared dx. And then my total volume, I'm going to add up all the slices from as far left as x equal to -5 and as far right as x equal to +5. So then we pull out the 1/2 pi, we integrate this, and we get 25x minus x cubed over 3 from -5 to 5. We get 1/2 pi times, we plug in 5, we get 25 times 5, which is 125. minus 5 cubed, which is 125 over 3, minus, if we plug in negative 5, we get negative 125 minus negative 125, so plus 125 over 3. And that's, I would probably leave it like that, but if you want to simplify it, it's going to be 1/2 pi times, again, something minus a third of something is 2/3 of something. That's going to be 2/3 of 125. And that's also going to be 2/3 of 125 because you have really plus 125 minus 125 thirds. So again, plus 2/3 of 125. So that's going to be, distribute the 1/2, or 2/3 plus 2/3 is 4/3. So you get 1/2 times pi times 4/3 times 125. Cancel a 2 here and a 2 here. So 2 times 125 is 250. So you have 250 pi divided by 3. Cool. Oh, this last problem. Okay. A patient is continually receiving a drug through an IV drip. If the drug is eliminated from the body over time, so the fraction that remains after T hours is e to the negative 0.3 T. At what constant rate, so we're trying to find R of T, should the drug be administered to maintain a fixed level of the drug in the bloodstream? Okay, so we have our P of T equal to P naught times S of T plus the integral from 0 to T of S of T minus T times R of T dt. So what we're saying here is the drug is eliminated in the body so that the fractions that remain, okay. We want to maintain a fixed level of the drug in the bloodstream. So what that means is that whatever P naught is, that is what P of T should also be, regardless of what T is equal to. That's kind of the trick here, is that P of T is kind of interesting. I feel like I'm forgetting something. Let me think about this for a second. No, I think that seems right. Okay, so yeah, that's right. We're trying to find R of T. So we're going to say that P naught is equal to P of T. Right. So we're going to have P naught equal to P naught times S of T. S of T is e to the negative 0.3 capital T plus, we're going to write this as the interval from 0 to T. S of T minus T is going to be e to the negative 0.3 times capital T minus T. And again, R of T is a constant, so we're just going to write R so we can solve for it. Okay. So working towards solving for this as well as simplifying, I'm going to bring this over here. So I have P naught minus P naught e to the negative 0.3 capital T. And I really feel like I'm forgetting. Let me double check one thing real quick, just so I don't go down the wrong path here. I think I'm doing this right, but I feel like I didn't think about it all that well. So I'm just going to check something real quick. Maybe. Sorry. There we go. Apologies. Um, Let me just look here real quick. Sorry, this is okay. One moment. Okay. No, I've totally got the right idea. Just want to make sure I wasn't crazy. Okay, cool. Right on. So over here, we're gonna pull out the R, or sorry, equals. We're gonna pull out the R and also the e to the negative 0.3 times capital T, because capital T is a constant. And we're left with the integral from 0 to T of e to the negative 0.3 times negative T, so e to the 0.3 T. Okay, a little more simplifying. So let's factor out the P naught here. So P naught times 1 minus e to the negative 0.3 T equal to R times e to the negative 0.3 T. And then we're going to integrate this. So when you integrate e to the 0.3 T, you're going to get e to the 0.3 T divided by 0.3. So it's going to be 1 over 0.3 times e to the 0.3. I'm just going to do it So it would be e to the 0.3t, we'd plug in t, and we subtract and plug in 0. That's going to be e to the 0.3t minus e to the 0.3 times 0, which is 1. Okay. So I always feel like I blow it here. Let's go ahead and distribute the e to the negative 0.3t to this. So I multiply this specifically to here. Look what happens. I have p naught times 1 minus e to the negative 0.3t equal to r times 1 divided by 0.3 times e to the negative 0.3t times e to the 0.3t is e to the 0. And e to the negative 0.3t times 1 is e to the negative 0.3t. Hey, look, that is the same as that. And if we divide both sides by that, they're going to cancel. So we're left with p naught equal to r divided by 0.3. And solving for r, we get that p naught times 0.3 is equal to r. So the constant rate that we should be administering the drug to maintain a fixed level of drug in the system is 30% of whatever the initial amount was. Interesting. Yeah. Let me just double check that one more time to make sure it doesn't sound too crazy. Yep, no, that's exactly how it looks on the other one. Yeah. So that is the practice exam. I'll double check and make sure that those typos are fixed, and good luck on your exam. Well, I'll see you on Tuesday. Make sure you come to co-class on Tuesday with questions, and then good luck on your exam on Wednesday. Bye.